Section 2-3, the limit theorems. The objective of this section is using the limit theorems, be able to state them, use them in a proof, and explain why they are true. So let's take a look at these limit theorems. These are on page 42 in your book. To get started, we're going to use these two limits here throughout. So I just want to define them once and then not have to define them over and over again in each of these theorems. So we're going to let L1 be the limit as x goes to c of g of x. And we're going to let L2 be the limit as x goes to c of h of x. Okay, so let's take a look at the first theorem here. This is for the limit of a product of functions. So it says the limit as x goes to c of g of x times h of x. There's the limit of a product. Turns out that's equal to the limit as x goes to c of g of x times the limit as x goes to c of h of x. Or in other words, that's equal to L1 times L2. So notice what we were able to do there. We were able to take the limit of this product of h times g and rewrite that as the product of the limits of h and g. In other words, another way that we could read this off, and we'll kind of use this verbiage several times here with these properties, is the limit of a product equals the product of the limits. Limit of a product equals the product of the limits. It's a nice way to remember that. Let's take a look at the next property here. This one is for the limit of the sum of functions. So this one says the limit as x goes to c of g of x plus h of x is equal to the limit as x goes to c of g of x plus the limit as x goes to c of h of x. Or in other words, that's equal to L1 plus L2. So again, it's saying here that I'm taking the limit of a sum of these two functions, g and h, and I can rewrite that as the sum of the two individual limits, the limit of g and the limit of h. So another way to read that off, similar to the verbiage we just set up above, is the limit of a sum equals the sum of the limits. Limit of a sum equals the sum of the limits. All right, let's take a look at the next property. This one's for the quotient of two functions, limit of a quotient of functions. So here we have the limit as x goes to c of g of x over h of x. Turns out that's equal to the limit as x goes to c of g of x divided by the limit as x goes to c of h of x. Or in other words, that would be equal to L1 over L2. L1 divided by L2. Of course, L2 cannot be 0 in this scenario. We have to handle that a slightly different way. So again, to look at what we're saying here, I have a limit of a quotient, and we're saying that's equal to this quotient of these two individual limits. Or again, put that in words, a nice way to remember that. The limit of a quotient equals the quotient of the limits. Okay, let's take a look at the next one here. This is for a constant times a function, the limit of a constant times a function. We're going to call our constant here k. So we have the limit as x goes to c of the quantity k times g of x. K is our constant, our function is g of x there. It turns out that's equal to the constant k times the limit as x goes to c of g of x. Or in other words, that would be k times L1. So what we're saying here is if we have a limit of a constant times a function, we can rewrite that as the constant times the limit of our function. So that's the way that we might remember that here. In words, the limit of a constant times a function equals the constant times the limit. All right, the next property is our identity function. The limit of the identity function. Now, the identity function is the function y equals x. We call it the identity function because of the fact that whatever you plug in for x, that's the exact same thing you get out for y. That's the identity function. So if we're taking the limit as x goes to c of our identity function, which would be just x, limit as x goes to c of x, turns out that's just equal to c. And again, if you remember the definition of a limit, the limit was the y value that you're approaching. And so because of the fact that we're letting x approach c here, that means that our y value is approaching the exact same value because it's the identity function. Whatever x is going to, y is going to that same value with the identity function. In other words, we can say the limit of x is just equal to c. Anyway, one last theorem here to consider, and that's the limit of a constant function. And we'll call k our constant here, so we're talking about y equals k. Graphically, that would just be a horizontal line. Y equals k. So it turns out that the limit as x goes to c of our constant k ends up giving us just k. Now again, if you go back to the definition of a limit said that the limit is the y value. And if we're talking about the constant function, it's just a horizontal line, so therefore our y value is the same. It's equal to k everywhere. It really doesn't matter what x is approaching. We're always going to approach the same value of k every single place. So that's why the limit turns out to be k. Or in other words, we can read that off here as the limit of a constant equals the constant. Now you'll notice these last two theorems are the only two theorems that show us how to get rid of that limit notation. In all the previous theorems there, it just showed us how to rewrite one limit in terms of another limit. But when we get to these last two, you start out with a limit on the left side, but you'll see that on the right side, for example, for the identity function, there is no limit over here on the right side. We're done with the limit. We've evaluated it. The same thing happens over here for the limit of the constant function. Notice over here on the right side, there's no limit left. We have evaluated it. That's the whole goal here. To break these problems down until we have either just the identity function or the constant function, and then use this property to get rid of the limit notation. That's going to be the process that we go through here. So let's take a look at an example and use these properties along the way. Take a look at example 1. It's on page 42. It says to use the limit properties to prove that the limit as x goes to 3 of x cubed minus x squared minus 2x minus 12 all over x minus 3 is equal to 19. All right, so let's write down this limit here. The limit as x goes to 3 of x cubed minus x squared minus 2x minus 12 divided by x minus 3 equals 19. Well, first of all, the first thing you should notice here is they're obviously not asking you to find the limit. They came right out and told you what the limit is. The limit is 19. This problem says to use the properties there to prove that it in fact is equal to 19. So that's going to be our goal. Okay? And we're just going to break this down step by step until we can actually find what the limit, or prove that the limit of this thing is equal to 19. And our goal is, again, to eventually get it broken down all the way until we have just the limit of the identity function or a constant function, those last two properties that we saw. but we'll use the previous properties along the way to get us to that point. All right, the first thing that we have to do with this problem is we actually need to simplify this a little bit. And it turns out in this function that we're starting with here, that x minus 3 is obviously a factor of the denominator. That's the only factor I see. Turns out it's also a factor of the numerator. And you can check that out by plugging in 3 in the numerator. You'd have 3 cubed minus 3 squared minus 2 times 3 minus 12. If you calculate that out, you'll get 0. Okay, 27 minus 9 minus 6 minus 12 gives me 0. So the fact that I find a 0 in the numerator tells me that I have found one of its, not only one of its zeros obviously, but it's also one of its factors. So what I want to actually do is factor out the x minus 3. And I'm going to use synthetic division here to help us see how to do that. So there's several ways that you can write the synthetic division symbol out here, and I'm going to do it this way. Write down the coefficients of the numerator. So the coefficients, you have 1x cubed, you've got a negative 1x squared, a negative 2x, and then a minus 12. And I like drawing it like this and put my division sign here. It's kind of an upside down division sign there that we represent that with. And the number that goes out front is the value that you're subtracting from x in the denominator. It's x minus 3, so I'm putting the number 3 out front. All right, and then through addition and multiplication here we can evaluate this. I'm going to add the 1 plus the nothing below it here to get 1. And then I multiply by the 3 out front. So the 3 times the 1 I just wrote down gives me 3. And then I repeat this process. Add, multiply, add, multiply. So negative 1 plus the 3 gives me 2. 3 times 2 is 6. Negative 2 plus 6 is a positive 4. And 3 times 4 is 12. Negative 12 plus 12 gives us 0. And that's what we're hoping to come up with here. If I'm saying that that x equals 3 is a 0 of this thing, then the remainder, when I divide by x minus 3, better be 0. And that's what I'm getting there. Now the other part here, the 1, 2, 4, those are the coefficients of the other quadratic term here. So I'm going to just rewrite this problem first of all. So we have the limit as x goes to 3 of, by factoring out or dividing out by this x minus 3, I found one of its factors here is x minus 3. The other factor then is x squared plus 2x plus 4. Again, those come directly from the fact that I have a coefficient of 1 here in front of the x squared. Got a coefficient of 2 in front of this x term, and my constant at the end is the 4. So those come directly from the values there. That's the numerator of this thing. And the denominator is x minus 3. And now you can see that because I have a common factor in the numerator and denominator, I can cancel those out. All right? And I'm going to just put on here, off to the side, I'm going to list what properties we're using along the way. And I'm going to list that this was just some algebra is all we've basically done here. We haven't used any of the properties, but I'll just indicate that that's what we've done. You don't necessarily have to indicate that, but I'm going to go ahead and write it down here so we understand what we've done in that first step. And I'm just going to rewrite this so that I've got the limit as x goes to 3 of the quantity x squared plus 2x plus 4. That's all that's left after we do our synthetic division and factor out. All right, so now let's use some of our properties. I see I have the limit of the sum of 3 terms, x squared, a 2x, and a 4. Well, I have a sum property that tells me how to rewrite that. So I'm going to rewrite this as the limit as x goes to 3 of the following. Our property was the limit of a sum is equal to the sum of the limits. So it's the limit as x goes to 3 of x squared plus the limit as x goes to 3 of 2x plus the limit as x goes to 3 of just 4. And I'm going to write over to the side here the property that we use. That's our sum property. Okay, let's take a look at the next step here. The x squared, I can think of x squared as being x times x. Let me just write that just here above it, x times x. That's what x squared is equal to. So I don't have a property for powers, but I did have a property for product. So I'm going to handle that one that way. And I also am going to take care of this 2x here with the fact that 2x, of course, is a constant times a function. So I'm going to use my two properties in order to rewrite this. So let's take and deal with the x squared, or the x times x first. Our property was the limit of a product is equal to the product of the limit. So I can rewrite that as the limit as x goes to 3 of x times the limit as x goes to 3 of x. Limit of a product is equal to the product of the limits. We'll add that to. I'm going to go ahead and take care of this middle term here at the same time. But here we've got a constant times a function. So our property was the limit of a constant times a function is equal to the constant times the limit of the function. So it's 2 times the limit as x goes to 3 of x. And at the end there, I'm just going to leave that last term there alone. It's already the limit of a constant, and we have a way to evaluate that. So we used, first of all, the product property here. And I'm going to abbreviate the next property that we used was a constant times a function. Let's say CONST times FUNC for constant times a function. You can abbreviate it the same way as you're writing these out. And now if you look at what I'm left with, I have the limit of the identity function times the limit of the identity function. Those I know how to evaluate. Those are the last two limit theorems we talked about. Those are the goal. Get them to those two properties. Here in the middle here, I've got the limit of the identity function again. I know how to take care of that. And at the very end, I've got the limit of just the constant function. I know how to take care of that. So use those last two properties now. So the limit as x goes to 3 of x. That's our identity function, so the limit is heading towards 3. Limit as x goes to 3 of x. Again, that's the identity property, so that limit is equal to the constant. It's equal to 3. We'll add that to 2 times. The limit as x goes to 3 of x. That's, again, our identity property. That limit is heading towards 3. Whatever x is going to, y is going to the same thing we said. And finally, at the very end, we have the limit as x goes to 3 of 4. That's our constant function. So we said in that case, it's heading towards that constant. Limit of a constant is equal to the constant. And let's indicate what properties we've used here. We first used our identity property. And then we used our constant function property. So the identity function property and then the constant function property. And now if you see what you're left with, 3 times 3, of course, is 9. 2 times 3 is 6. And the 4 at the end, 9 plus 6 plus 4 sounds like 19. That's what we were trying to show. You want to be able to do the exact same thing in some of these problems that you're going to see in your assignment. And that is the end of this section for us.